Preparing for a nuclear safety engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain defense in depth in nuclear safety, and why is it important? Defense in depth means I never depend on one protection layer to keep the plant safe. I look at multiple physical and procedural barriers: fuel matrix, cladding, reactor coolant boundary, containment, engineered safety systems, operator actions, and emergency planning. Each layer either prevents an event, detects degradation, or mitigates consequences. The value is resilience. If one barrier fails, independent backups still protect workers, the public, and the environment. While answering, focus on layered barriers: prevention, detection, mitigation, containment, redundancy, independence, and how defense in depth reduces reliance on any single system or human action. Question 2. What does ALARA mean, and how would you apply it during plant maintenance? ALARA means keeping radiation exposure as low as reasonably achievable, not simply below limits. For maintenance, I would start with dose history, surveys, source term information, and a clear radiological work plan. Then I reduce time through mock-ups and sequencing, increase distance using remote tools, and add shielding where practical. I also monitor dose during the job and stop if conditions differ from assumptions. ALARA is disciplined planning plus field feedback. Make sure to cover time, distance shielding, pre-job planning, dose estimates, radiological work permits, contamination controls, mock-ups, real-time monitoring, and balancing dose reduction with operational practicality. Question 3. How do deterministic safety analysis and probabilistic safety assessment differ? Deterministic analysis asks, can the plant survive defined accidents under conservative assumptions? It focuses on design basis events, acceptance criteria, margins, and engineered safety performance. Probabilistic safety assessment asks, how likely are accident sequences and what drives risk? It uses event trees, fault trees, failure probabilities, and uncertainty. I use deterministic analysis to prove minimum safety capability and PSA to prioritize improvements, identify weak links, and support risk-informed decisions. In your answer, talk about conservative bounding assumptions, design basis accidents, event frequencies, core damage frequency, risk insights, uncertainty, and how both methods complement licensing and decision-making. Question 4. Walk me through your safety response priorities during a loss-of-coolant accident scenario. In a LOCA, the immediate safety goal is maintaining core cooling and containment integrity. I would confirm automatic reactor trip, safety injection, or emergency core cooling actuation and containment isolation. Then I track reactor pressure, coolant inventory, core exit temperature, sump conditions, and containment parameters against emergency operating procedures. Operators should stabilize the plant, avoid conflicting actions, and communicate clearly with technical support and emergency response teams. Fuel cooling drives every decision. Be sure to mention reactor trip, emergency core cooling, heat removal, containment isolation, pressure and level monitoring, emergency operating procedures, communication, and protecting fuel integrity. Question 5. What does a strong nuclear safety culture look like in day-to-day work? A strong safety culture shows up before anything goes wrong. People challenge assumptions, follow procedures, document anomalies, and feel safe raising concerns. Leaders reward conservative decisions, not just schedule performance. I expect independent verification for critical steps, clear pre-job briefs, and stop work authority when conditions change. The best plants learn from small signals, near misses, and external operating experience, because waiting for a major event is unacceptable. While answering, include questioning attitude, conservative decision-making, procedural adherence, reporting culture, leadership accountability, independent verification, stop work authority, learning from events, and avoiding production pressure. Question 6. How would you perform a hazard analysis for a new nuclear plant system or modification? I would begin by defining the system function, boundaries, interfaces, operating modes, and safety classification. Then I would identify hazards using tools like HAZOP, FMEA, checklists, and operating experience. For each credible failure, I assess causes, consequences, existing controls, detection methods, and required mitigations. I pay special attention to common cause failures and dependencies like power, cooling, and instrumentation. The output should be traceable actions, owners, due dates, and verified closure. Make sure to cover system boundaries, functions, failure modes, initiating events, HAZOP or FMEA methods, consequences, safeguards, common cause failures, assumptions, documentation, and action tracking. Question 7. What are the key safety requirements for a reactor protection system? A reactor protection system must detect unsafe plant conditions and rapidly place the reactor in a safe state. I expect redundant sensors, independent logic channels, reliable actuation, qualified equipment, and fail-safe behavior where loss of power or signal drives a safe response. Set points need proper margin, configuration control, and periodic surveillance testing. I also separate protection from normal control to prevent a control failure from disabling protection. Independence and testability are essential. In your answer, discuss automatic trip functions, redundancy, diversity, independence, fail-safe design, surveillance testing, set point control, reliability, cyber considerations, and separation from non-safety control systems. Question 8. How would you evaluate whether an emergency preparedness program is effective? I would evaluate emergency preparedness by testing whether the organization can classify events, notify authorities, assess radiological consequences, and recommend protective actions within required timelines. Drills should include realistic equipment failures, incomplete information, shift turnover, and coordination with off-site agencies. I review emergency action level use, command roles, communication logs, dose projection quality, and corrective actions from critiques. A good program proves capability under stress, not just compliance on paper. Be sure to mention emergency action levels, classification, notification timelines, drills, dose assessment, protective action recommendations, command structure, communications, critique process, training, and coordination with off-site authorities. Question 9. Describe how you would conduct a root cause investigation after a safety-significant event. After a safety-significant event, I first stabilize conditions and preserve evidence: logs, alarms, trends, procedures, work packages, and physical components. Then I build a timeline and interview personnel, using a fact-finding, non-blaming approach. I use methods like barrier analysis, change analysis, and causal factor charting to separate symptoms from root causes. Corrective actions must address technical, human, and organizational contributors, include extent of condition review, and later be checked for effectiveness. While answering, focus on preserving evidence, event timelines, interviews, causal analysis tools, human and organizational factors, extent of condition, corrective actions, effectiveness reviews, and avoiding blame. Question 10. What controls are important for preventing a nuclear criticality accident? Criticality safety is about preventing an unintended self-sustaining chain reaction. I control parameters such as fissile mass, geometry, concentration, moderation, enrichment, spacing, reflection, and neutron absorbers. The double contingency principle is key. At least 2 unlikely independent failures should be required before criticality is possible. I also rely on posted limits, engineered favorable geometry, independent verification, criticality alarm coverage where needed, and strong operator training. Administrative controls alone are weaker than engineered controls. Make sure to cover mass, geometry, moderation, enrichment, reflection, spacing, neutron absorbers, administrative limits, double contingency principle, criticality alarms, training, and independent verification. Question 11. How would you approach radiation shielding design for a work area? I would start by characterizing the source: radionuclides, activity, energy spectrum, geometry, operating duration, and whether gamma, beta, or neutron radiation dominates. Then I apply dose criteria, occupancy assumptions, and ALARA targets to choose shielding materials. Lead or steel may work for gamma. Hydrogen-rich materials and absorbers are often needed for neutrons. I also check penetrations, streaming paths, activation, access needs, and maintenance impacts. In your answer, include source characterization, gamma and neutron differences, occupancy factors, dose limits, ALARA targets, material selection, streaming paths, buildup, activation, verification surveys, and maintainability. Question 12. How do you manage aging and degradation of safety-related structures, systems, and components? Aging management starts with knowing which components are safety-related and what degradation mechanisms apply. Corrosion, fatigue, embrittlement, wear, thermal aging, radiation damage, or cable insulation breakdown. I use inspections, surveillance tests, condition monitoring, and performance trending to detect degradation before function is challenged. Maintenance should be risk-informed, not purely calendar-based. I also watch obsolescence and environmental qualification. The goal is preserving design basis capability throughout plant life, including extended operation. Be sure to mention aging mechanisms, environmental qualification, inspections, surveillance testing, condition monitoring, trending, preventive maintenance, obsolescence, safety significance, corrective action, and license renewal expectations. Question 13. What human factors issues do you consider when reviewing nuclear operating procedures? Procedures should help operators succeed under pressure. I look for clear entry conditions, unambiguous steps, correct sequencing, cautions before critical actions, and good placekeeping. I check whether independent verification is required for irreversible or safety-significant steps. Human factors also include workload, alarm burden, time pressure, control room indications, and possible error traps. Before approval, procedures should be validated through walkdowns, simulator runs, or tabletop exercises with actual users. While answering, discuss clarity, step sequencing, placekeeping, independent verification, alarm response, workload, stress, control room layout, error traps, validation, operator training, and procedure use expectations. Question 14. How would you review a proposed plant modification for nuclear safety impact? For a modification, I first ask what safety function could be affected and which design basis or licensing commitments apply. I review drawings, calculations, set points, interfaces, failure modes, and impacts on redundancy, separation, qualification, and surveillance. Configuration management is critical, so procedures, training, spare parts, and maintenance documents must change consistently. I would require appropriate testing and regulatory screening before turnover. A modification is safe only when the whole plant configuration remains controlled. Make sure to cover design basis, safety classification, licensing basis, failure modes, interfaces, configuration management, procedure updates, testing, regulatory screening, training needs, and post-installation verification. Question 15. How do you ensure ongoing compliance with nuclear regulatory requirements and the plant licensing basis? Compliance requires more than knowing the rules. It requires controlled execution. I would maintain traceability to technical specifications, license conditions, safety analysis assumptions, commitments, and surveillance requirements. Changes should go through formal screening and approval, so the licensing basis is not unintentionally altered. Audits, self-assessments, corrective action trends, and reportability reviews help catch drift early. When issues arise, I prefer timely, factual communication with regulators, supported by clean documentation and corrective actions. In your answer, talk about technical specifications, license conditions, commitments, audits, surveillance requirements, corrective action programs, configuration control, reportability, change control, documentation, and regulator communication. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.